Okay, hello to everyone. We are going to start a seminar in which four researchers from different parts of the world came to the University of Granada to give some talks about the topic they usually work. So, in principle, these speakers will be Antonio Alex-Amor. He comes from the United States. María Garcia, she comes from United Kingdom. Miguel Beruete, he comes from the Public University of Navarra. And Mário Silveirinha, who comes from Portugal, from Lisbon. So first of all, I would like to thank the Spanish URSI because they have support this seminar and they have published the information in the social networks and they have sent information to everyone. So thank you very much to his president. In fact, the president is here, and I would like to let him talk or say some words in order to thank him the presence. So, Mikel.
No, thank you, Carlos, and the rest of the group in Granada. I'll keep my introduction very brief. Welcome, everyone, to this special technical day organized by the Smart and Wireless Applications and Technologies Group at the University of Granada with support of URSI Spain. As I said, I'd like to thank Carlos and the other group members in Granada for bringing us together today to explore the latest advances in photonics, radar, and telecommunication systems, fields that, as you well know, lie at the very heart of modern technology and communications. As Carlos has advanced, today's program features leading expert and pioneering researchers who will present innovations and insights on topics such as non-Foster circuits, GPR-SAR systems, smart metasurfaces, and chiral gain photonics, with contributors from the US, UK, Spain, and Portugal. I think this is a very unique opportunity to connect, learn, and discuss future developments that will shape these critical areas in the future. And I'm very happy to see you all in person or online in what promises to be a seminar filled with valuable changes. And that's it. Thank you to the University of Granada for involving URSI in this event. And thank you all for attending. Enjoy the talks.
Thank you very much, Mikel. We will. I would like to remind that we will upload the video because this is recorded. We will upload the video to the URSI channel on YouTube and the other networks associated with URSI. So let's start. First speaker is called Antonio Alex. He comes from University of Pennsylvania, and he will give a talk related to non-Foster circuits and stabilization purposes. So thank you, Antonio. Please.
Well, thank you, Carlos. Can you hear me?
Quédate tú si quieres.
Okay. So, well, first of all, I would like to naturally thank Dr. Carlos Molero, Professors Pablo Padilla and Juan Francisco Valenzuela for holding this event here at the University of Granada. I would also like to thank, naturally, Mikel Lasso and Adrián Amor for promoting the event, which I think that it will be really interesting. And thank you, naturally, for inviting me. Okay, so this talk will be related to the study of non-Foster circuits and the inclusion of time modulations. This work has been done at the University of Pennsylvania. I've been a postdoctoral researcher there. And actually, it has been supervised by Professor Nader Engueta. And it also counts with the collaboration of my colleague, Grigory Pititsins, who is a postdoc there, actually a good friend. So technical difficulties now. No. Nope. I think it's working now. Okay, so the concepts that I will be discussing here, they are framed within the emerging topic of space-time, photonics, and metamaterial. As you know, this has been a hot topic in the area of electromagnetics during the last maybe 5-10 years, especially during the last 5 years. And this is due to the fact that time-modulated systems offer possibilities that conventional passive systems cannot. For instance, one of the things or 3 interesting applications or capabilities that these systems offer are the creation of non-reciprocal responses. It has been naturally really tough to do with, and it has been naturally or normally done with magnetic materials or magnets, which actually are bulky and difficult to build. And also the implementation of efficient beamforming and frequency mixing, because actually a temporal modulation in electromagnetics translates directly into a frequency conversion. So frequency conversion is a natural feature of this kind of systems. And this application has been really useful for the development of future communication systems. In this sense, I would like to mention some previous contributions that we have done here at the University of Granada. We have been normally studying systems that alternate in time between different states, normally metal states and fully transparent or fully reflective states. We have some works like the first one that you can see. The second one, time periodic metallic metamaterials, which are an extension of the first work. In this third work, essentially, we include spatial modulation as well, because the previous ones were only related to temporal features. And we have also done a collaboration with Professor Silveirinha that actually he will be giving an excellent talk later. I wanted to mention that because these topics and these works, some of them are part of the doctoral thesis of the doctoral student Salvador Moreno, who actually will be defending his thesis tomorrow here at the University of Granada. So I invite you to take a look at his work, which is good. And actually, it has been supervised by Dr. Carlos Molero and myself. Okay, so going to my current work at the University of Pennsylvania, I've been working under the supervision of Professor Nathan Engeta. He's a high-profile person in this field. I've been working in different topics in 2 different projects, actually, that they came from my main funding over there. One is related to the topic of analog computing. As you know, this has become popular. People are working with waves to implement mathematical operations like matrix inversion, simple multiplication products, image processing. I've been working in this topic, especially in the part of designing incoherent systems that they avoid or they not include the use of phase. But the current topic, the second topic or the second project that I've been involved in is the project related to space-time photonics, which is actually what I will be explaining here. We have done different things with metamaterials and media in general, but I will be discussing here the application to circuits, specifically to non-Foster circuits. Okay, so our goal here in this talk is to study the effect of including time modulations in conventional circuit elements like inductors, capacitors, to see if we can stabilize the circuits. I will mention them, and if we can extract some interesting features of that. We will focus on a simple example, which is a LC resonator, where the inductor is time modulated and the capacitor is negative. I will discuss what a negative capacitor means. And the 3 main works or keywords in this talk will be non-Foster, time modulations, and stabilization, because these are the key things that we will discussing here. Let's start by reviewing which is a non-Foster circuit, because this is actually important. So Foster's reactance theorem, you may know it, essentially says that the reactance, remember that the reactance is the imaginary part of the impedance of a passive circuit element, like a conventional inductor or capacitor, has to monotonically increase with frequency. Increase with frequency in the case that we work with the engineering convention, with e to the plus j omega t. If we work with the physics convention, it will be the opposite. This is really straightforward from a mathematical perspective. If we compute the derivative and the derivative is positive, we can check that the element is Foster, sorry, in this sense. Examples of Foster-like components: a conventional inductor, we can see that the reactance is omega L. It increases with frequency, and a conventional capacitor, the reactance of a conventional capacitor also increases with frequency in the negative and in the positive frequencies. Okay, so but there is a class of elements which are called non-Foster. Non-Foster because they don't fulfill Foster reactance theorem. They are active elements, and this is the key because the other ones are passive, which has interesting properties. I will discuss them. But let's go first for a simple example of a non-Foster element, which would be a negative capacitor. When I say negative capacitor, this is a contraction of maybe a better way of saying it could be a capacitor with negative capacitance, okay? But I will contract it and say it as a negative capacitor. If we plot the reactance of a negative capacitor, we can see that it doesn't increase with frequency releasely. So this would be a simple way of checking that it is a non-Foster component. It may seem crazy, the implementation of negative elements, but this is a topic of a long history. Actually, there are patents from the 1923 where they are starting to implement or propose ideas to implement negative impedance components, like negative resistors, negative inductors, and negative capacitors. I will be discussing here theoretical things, but we don't want to lose track of reality in the case that we want to implement an experiment. So a negative capacitor can actually be done, I wouldn't say straightforwardly because I'm not expert in experiments, but it can be done by cross-coupling transistors. So in that way, with systems or circuits of this kind, which are not extremely difficult, we can obtain no, it's not working. Now, so we can, by cross-coupling transistors, like we can see here, we can see that we can achieve, for instance, negative capacitances of -2 picofarads in that case. And they can be achieved in a wide band in the case that we want to implement more sophisticated implementations. Okay, so what are the advantages of this kind of system? The advantages are that non-Foster elements are active elements. So they have the advantages of active elements. What are the advantages of active elements? That they are not restricted by passive bounds, passive circuit bounds. For instance, there are two famous bounds, which are Bode Fano and also Carli-LaRosa. Carli-LaRosa, essentially, they extended the concept that Bode and Fano were discussing over there. But the bandwidth, we normally, and we understand that the passive of the bandwidth of a passive matching network is limited, and we know that. So with non-Foster circuits, we can overcome that. And there are examples of this. We have two panels over here. Maybe we can focus on the right panel, where we can see that the red curve, which is related to a non-Foster matching network, it really increases the bandwidth. Actually, this is for sound pressure levels. It's not even for electromagnetics, but it doesn't matter. This can be applied in electromagnetics and in other fields as well. The problem of non-Foster components is that they are active and they have the problems derivated of active elements, like stability, for instance. And this is a good moment to explain the concept of stability that we will be using here. So if we fit a system with a bounded input, we would say that the system is stable if the output is also bounded. If we have an output of this kind, like the red curve, we would say that the system is unstable. And we will be using this concept along the whole presentation. Non-Foster networks suffer from this kind of problems, and they have to be stabilized prior to operation. So we can use it, because otherwise the circuit will blow, essentially. Which is our motivation here, because our goal here is to study the enclosing of time modulations to stabilize non-Foster circuits. Our motivation here is that we actually know that there are other kind of materials or systems in nature, in biology, in mechanics, that they can become stable when they were originally unstable. They can become stable if we perturb their parameters. The parameters can be position, frequency, amplitude, but we know there are systems of this kind and in other fields. Actually, a really interesting example of that I would like to present you is what is called Kapitsa's pendulum. Kapitsa's pendulum, it's nothing really complicated. It's simply a conventional pendulum that where we add a mechanical base which is vibrating horizontally or vertically. So it is essentially like a conventional pendulum where we position the ball close to the upper position, and after that we vibrate the base. So if we do that, we are adding a perturbation through this mechanical base, and Kapitsa showed that the system can become stable. For instance, there is a GIF that shows that the system is unstable, as you see, the ball falls, but when you are the mechanical vibration, you can stabilize the ball, the mass, you can stabilize it in the upper position. So you are creating an stability point where it doesn't exist. And actually, this is a mechanical temporal vibration. So, I mean, we were thinking, okay, why can't we do that in circuits or something similar to that? Well, let's review some quick things about Kapitsa's pendulum. Well, Kapitsa's pendulum is called this way after the physicist Piotr Kapitsa. Actually, he was a Nobel Prize awardee. So he derived the physics of that in the 1951. Well, we have the motion equations, where essentially simple trigonometry plus f of t, which is the mechanical vibration. In our case, is sinusoidal, and this is important because we are not adding a control. It's a control thing, and we are it's a simple sinusoidal modulation. It's nothing crazy. We can compute the differential equation through the Lagrangian or through the Newtonian mechanics. Is the same. The Lagrangian is this, and the differential equation for the angle theta in the pendulum will be this thing, essentially, over here. So it's the same. It's the same equation that in a conventional pendulum plus this term, cosine term, which is introduced after adding this mechanical vibration. Actually, we can see that, well, it can be clear. If we don't pay attention to the modulation, we have a minus omega naught term, which essentially says that if you position the ball in the upper position, it's going to be unstable, because this is a simple differential equation. But if we add this mechanical vibration, we can create a new stability point in the upper position. And this is quite interesting. Actually, Kapitsa showed that this happens if you overcome a limit frequency, which actually has an analytical expression which is not particularly difficult to see. So let's go back to the non-Foster LT circuit, where we have a time-modulated inductor and a negative capacitor. So the differential equation that models that for the current in the circuit is this one. It can be extracted with by applying Kirchhoff's law, essentially. Nothing spectacular in this sense. And let me remark that if we put a constant value for the modulation, then we recover the conventional formula of a LC resonator. And this is interesting because we will be using that in the future. So in this scenario, for this simple differential equation, it can be clearly seen that the stability of the system actually depends on the value 1 over omega L naught C. If this term is positive, the system is stable with a periodic solution. The frequencies are complex, and the complex frequencies create a cosine modulation, essentially. But if one of them is positive and the other is negative, then the system is unstable. So essentially, the system grows with an exponential increase. There are two ways, by the way, of stabilizing the circuit, if you see it, and we will be using that. You can place a positive L naught and a positive C, or a negative L naught and a negative C. And we will be using that as well in the future. I wanted to mention. The thing is that this differential equation, it's ordinary equation, second order, it's linear. Okay, that has many interesting things, but it's difficult to treat. Actually, it's lacks of analytical solution in a general scenario. So instead of working with the current, it could be a good option to work with the flux, with the magnetic flux that goes through the inductor. Actually, the flux is related with the current through the inductance L of t. Actually, this is not an approximation. This is simply a change of variable that can make things easier. So why is that? Because the differential equation for the magnetic flux is that it's way simpler than the one for the current. So instead of solving the differential equation for the current, we can solve it for the magnetic flux and then compute the current with this simple relation. Actually, this is way easier to study stability and other things that people like De Angelo in linear system of linear books related to linear systems, they have been studying that for other fields of science. There is an interesting connection between Kapitsa's pendulum, which I introduced before, and our circuit. And the connection it can be clearly seen. The differential equation is the same. We have a second derivative of the function, second derivative of theta, second derivative of phi, the magnetic flux. We have the function theta, the function phi, and we have a time varying coefficient, which is multiplying that. So as the modulation L of t can be the one that we want to choose, one modulation, which is quite interesting to use, is the modulation that mimics the response of the pendulum. Why is that? Because we know that the pendulum is stable. So if we use this modulation, the circuit should be stable as well. So how can we compute this modulation? By simply equating both terms. If you equate both terms, you can derive a modulation of L of t, which is not particularly difficult, that can give us stability in the system. Actually, let's test that. If we have a LC circuit with a negative capacitor of -1 millifarads, which is negative, and the modulation that we apply is really small, it's only 0.1, it's 10% of the total variation. If we are below this stability frequency, the L of t circuit, this is the current plot along the time, the current will be unstable. Why? Because we are not overcoming Kapitsa's limit frequency. But if we overcome this frequency, we can see that the non-Foster circuit with the time modulated L and the negative C becomes stable. And actually, it becomes stable following Kapitsa's trend, and there is an interesting one-to-one correspondence, but there is one slight difference. And the difference is that essentially the angle theta in the pendulum would be the envelope of the current. The current is like amplitude modulated. It's an AM modulation of the value of a theta. Actually, you can more or less see that there is a red curve up there, which will represent the magnetic flux, and the magnetic flux is associated to the angle theta. So okay, that's perfect. We have shown that we can stabilize the circuit. Great. But we have a problem with this modulation. And the problem is the following. The problem is the actual implementation of this modulation in a laboratory. Why is that? Because it has two impracticalities. First of all, it has singularities. This modulation goes to infinite, okay? Infinite and minus infinite. Maybe in a laboratory, you can place finite values, but large values, and mimic that. So maybe this is not the most important in practicality. The important one is the second one, which actually the modulation has to alternate between positive and negative values. And that's really complicated because L of t is essentially relating the magnetic flux with the current. So if we're in the positive amplitude, it makes that it says that the relation is direct. But if we are in the negative part, it means that if we increase the magnetic flux, then the current is decreasing. It would be like something crazy. And this is really difficult to implement in a laboratory. So can we think of another modulation? Because nothing prevents that we can find another L of t, which is also good to stabilize the circuit. So in that sense, there is a work that has been done by Grigory Pititsins, Sayad Mirmosa, Silvio Hrabar, and Sergei Tretiakov, that they introduce a really interesting concept. And this concept is that with time modulations of the elements, you can mimic other objects. You can mimic the response of other objects. So, for instance, can we use, in that case, a time-modulated positive inductance to mimic a negative inductance? Time-modulated positive to mimic a negative one. Why is that? Because we know that a negative inductance and a negative capacitor, it's going to be stable. So if somehow we can put a L of t that mimics a negative L equivalent, then we know that the system is going to be stable. So how do we do that? Well, if we want that two different elements behave the same, we need that their parameters are the same. So which are the parameters that we are working with in the circuit? Voltage and current, essentially. So if we somehow can make that the voltage across the time modulated one and the equivalent negative one is the same, and the current through the time modulated one and negative one is the same, voltage and current are the same, then both elements, even though they are different, they are going to behave the same in the circuit. I mean, it's a natural thing. So we can use the current voltage relation of both. You see that the green one is related to the time modulated one, the red with the negative static one. If we make both terms to be the same, we can integrate both terms and we can derive a modulation of L of t that give us a negative inductance. The problem with this is that we have I of t in the denominator, so we can have singularities as well. If we have if the current goes to 0, then the modulation goes to infinite as well. So we can avoid that, and I can present you the technical details later. We can avoid that by introducing a current source, a DC current source. So if we have the same system than before plus a DC current source, then we are mimicking or we are creating a modulation that can be positive. And that's the important thing. C1, by the way, is a constant of integration that comes after integrating both terms. And I is the value of the amplitude. So it is possible to select a C1 and I values that create a positive modulation. It's always positive. For instance, we are doing that over here. We have a modulation of L of t that you can see that it is clearly positive. And this modulation, which is more or less centered at 30 millihenries, it is mimicking an inductor of minus 4 milliamps. This positive one is mimicking a minus 4. So if we use the same capacitor, a negative capacitor than before, we will have somehow a double negative system, which should be stable. And we can see that the current I of t is stable in the circuit. We can clearly see. There are two different ways of obtaining stability. And actually, that will be the conclusion. We know that time modulations are, well, the whole field of space-time photonics is an interesting field that can give us many options. And in this case, we were trying to use temporal modulations to mimic responses that give us time invariant elements, for instance, in order to stabilize a non-Foster circuit. Why is that? Because non-Foster components can overcome passive circuit bounds. And this is really interesting. So we have found two modulations, and we have shown with these two modulations, we can stabilize the non-Foster circuit. But nothing prevents that there are more modulations that can also stabilize the circuit. And actually, the important thing is that we have shown that for circuits that's zero-dimensional schemes. They don't have space. But nothing prevents that these ideas can extend it to deal with transmission lines, which are space-time systems, or even 2D or 3-dimensional time-modulated systems. Actually, we are working on that with Professor Nader, and I think that we are in the correct path to obtain the interesting things. Okay, the details of this talk can be found in this preprint that we submitted to the archive very recently. Rapid science power stabilization of non-Foster circuits via time modulations. So you have the technical details there, and thank you for your attention. I'll be happy to discuss questions with you.
So it's time for question. Any question from the audience? From both sides, online and people here. Miguel?
Or I can give you this one, maybe?
So come here. I think it's better.
So thank you, Antonio, for the nice talk. Is this working? Okay. So thank you for the nice talk. So you were showing us that you can, I mean, the main point of your talk is that you can get negative inductance with time modulation. I assume that you are always assuming negative capacitance with this type of transistor circuits and so on. But then the question is, can you also have negative capacitance through time modulation and then having both elements negative with time modulation? Would this be interesting or?
Okay, thank you, Miguel. Well, first of all, let me remark one thing. This thing that you said maybe is one of the main points, but I think that we have even a more overall point, which is that we can stabilize non-Foster circuits because Kapitsa's formula is a different concept. But regarding your question, which is the second type of modulation that we have found, yes, actually they were showing Silvio Hrabar, Grigori Pititsin, Sergei Tretiakov. They showed that with a time modulated system element, because they put examples in circuits to make it that more accessible. You can use time modulated circuits to mimic even components of different nature. So you can use a time modulated inductor to mimic a static capacitor, or the opposite. You can use a time modulated capacitor to mimic a negative inductor. So yeah, nothing prevents that. The thing is that you have to use, in this sense, you have to use voltage current relations. So voltage current relations between one inductor and the other inductors are practically the same. So it's really simple to solve the differential equation and extract the modulation L of t. Actually, even the differential equation can be solved by simply integrating both parts. Maybe if you use circuit voltage relations in capacitor, which is inverted to the circuit to the current voltage relation of a capacitor, maybe the modulation that you get is more difficult, but nothing prevents that you can do that. So yeah, you're right. Even though I think that in the paper they were using resistors, time modulated resistors to mimic capacitors, for instance. So yeah, you can even change the nature of the circuit element that you can use, and maybe that would be interesting for using. Okay.
No, but it's just a mathematical curiosity because you have posed the equation in slide number 11, okay, but it's the equation to solve, and you have found kind of solution. But I was wondering what's happening if you get a solution in which the expressions inside the parentheses get zero. So because you have a subtraction, no?
Yeah.
And as far as I remember, you have something like theta double prime
Yeah.
equal to. So it is a really physical solution. Can you think a really
Ca-
physical solution in this sense?
Can we put the presentation? Well, there is actually there is an interesting thing related to that I haven't remarked. And if we go to the last modulation, which is the one that mimics the negative static one, C1 is a constant of integration. That means that there is not a single solution. There are infinite solutions.
Yeah.
So that's actually going in your direction. The thing is that you can use this fact because C1 is not a physical parameter. The current I is a physical parameter. It's a voltage source that current source that you can control. So you can use that to find the better C1 that fits you. And nothing prevents that going to the thing that Miguel was asking, that if you try to use a varactor or another kind of element, nothing prevents, and actually I think that would be the case, that you have also infinite solutions as well. So maybe that's one part, which is related to the second modulation, and related to the first modulation, which is this one, which is 1 over c, the cosine term, and the constant term, which is related to gravity in the pendulum. So I mean that's a mathematical solution. If you mean with physical that can be implemented in the laboratory, it cannot.
No, not that. If the solution have a physical meaning or something like that.
The physical meaning is would be to mimic the response of the pendulum.
Okay.
So if the pendulum is stable in the upper position, the circuit can be stable too. The physical meaning of this expression is to behave like the pendulum. Why is that? Because we know that the pendulum is stable.
Okay.
But maybe there is another biology system that has a different differential equation, and we can do the same, and we can find the one-to-one correspondence. So that would be the physical meaning of that.
Okay.
And actually, for us, it was interesting because it was a test to say, okay, we can stabilize the circuit. It wasn't crazy. It is something that can be done, but it's not good to put into practice, unfortunately, this one. So this is why we studied the modulation.
Okay. So thank you very much, Antonio. So
Thank you, Carlos.
let's give an applause. Okay. And next speaker. Is that fine? All right. Sí. Okay. Okay, so next speaker is María García-Fernández. She comes from Queen's University of Belfast in North Ireland, and she will talk about a key technology for detecting very explosive threats. So Maria,
Thank
your
you
time.
very much. Yeah, let's see, it works. Well, in my case, I decided to do not a so technical talk. So I will combine a little bit of trying to inspire the new generations into starting a research career and also showing you some of my works in radar mounted sensors. So starting with introduction, as you may imagine, I'm from Spain. I did my bachelor's, master, and thesis at University of Oviedo in the north of Spain. And apart from that, I traveled quite a lot to different universities and research centers abroad, which I think it's very useful to establish new connections and see how things work outside of your typical working environment. I was a visiting student at Stanford University. Then, after finishing the master's, I did a research stay at Microwave Vision Group in Italy, which probably you know it's a well-known company for antennas and antenna measurement systems. I was also at the German Space Center. Then I studied the PhD under the supervision of Professor Fernando Las Heras and Dr. Yuri Albrecht, who you may know very well as well. During the thesis, I did a research stay at Northeastern University in Boston and at the Netherlands Organization for Applied Scientific Research in the Netherlands. And then I continue after the PhD working at University of Oviedo for a couple of years as postdoc. I moved to Queen's first as visiting scholar in 2022. And since 2023, I work there as Marie Curie Research Fellow. My research career falls within the broad field of applied electromagnetics. And in particular, I have been working on four major lines. First, we have ground-penetrating radar systems on board UAVs, which is basically the core of the presentation I will deliver later. Then we also work on near-field antenna measurement systems using UAVs, aiming to measure antennas at operational conditions without the need of moving them to an anechoic chamber. Obviously, we don't have the same type of accuracy, but it's very useful in some applications. And since I moved to Queen's, I started working on computational imaging, which is basically like applying kind of compressive sensing, but at the physical layer. And for doing that, we use compressive antennas, which are usually implemented as metasurface antennas. So now, going into further details about UAV-mounted microwave sensing, when I started working on this topic back at University of Oviedo, as well, most of the results I'm going to show here are from that time, we basically decided to join previous research lines in the group in both radar and antenna measurement with the use of UAVs to develop what we call beyond the visible applications with drones. And in particular, as I said before, we work mainly in the detection of buried targets and in the measurement of antennas at operational conditions. We patented both ideas when I was doing the PhD, and since then we developed different prototypes of the technology. So now going to the a little bit more technical part. In the case of UAV mounted GPR systems, as you may imagine, our goal is basically to detect buried targets without interacting with the environment. Well, I divided this part of the presentation into these main points. First, a brief introduction to how a radar or a ground penetrating radar works, a little bit of description about the system, the methodology. I will show you some prototypes we have developed, and then I will discuss a little bit the experimental validation and our recent works in this topic. So starting with the first point, the motivation is that mine contamination is still a worldwide problem, especially now it's becoming even worse with ongoing conflicts. There are still thousands of casualties every year. And on top of that, mine detection still mainly requires a lot of manual labor. So this means that there's a huge risk for operators. In most cases, they just use metal detectors. So they are not able to detect low metal contact mines. There's obviously a low inspection speed and also a lack of discrimination between different targets. As most cases, they just know whether there's a possible metallic piece, which might be just a screw. However, with ground penetrating radar or radars in general, we can detect both metallic and dielectric targets, provided there's a good contrast with the surrounding media. However, the price to pay is that the technology is quite sensitive to the soil composition and to the clutter, which is basically any reflection from the environment, which is not coming from the objects you want to detect. There are mainly two different types of ground penetrating radar architectures. Forward-looking, in which the antennas look ahead of the vehicle at the standoff distance, and the looking GPR, in which the antennas are directly pointing downwards. In the first case, there's usually less clutter coming from the soil surface, but it suffers from some problems related to the resolution and the sensitivity, especially due to the long distances to the expected area. In the case of down-looking GPR, we have another problem, which is how can we keep a safety distance if we want to use this system for landmine detection? There were some initial prototypes using lightweight terrestrial robots, but they were still at very low speed, and obviously there's still a detonation risk. So that's why we decided speed, avoid the contact with the soil, and having more flexibility in the inspection. As I said before, we patented the idea back in 2016, and since then we developed different prototypes of the idea. Here, this is one of the first prototypes. It was a proof of concept working with a radar working at C-band, which is relatively high frequency for ground penetrating radar applications, but it was a very successful proof of concept to detect targets buried in dry, sandy soils. After we saw that the technology and the idea was working, we started trying to find how to improve the prototypes. So we developed a prototype with a different radar, a noise radar working from 600 megahertz up to 6 gigahertz, which enabled us to inspect different types of soils with very successful results. We also added a second receiving channel to increase the information gathered per measurement position. And then we got a contract from the Spanish MOD to develop further prototypes for them. And within that project, which was awarded to University of Oviedo, we also tested different architectures that I will show you later. Well, the project was called Safe Drone because you will hear me talking about Safe Drone later. So the main idea is to mount a radar on board a UAV. The radar flies autonomously over the area under inspection, collects radar measurements that are sent in real time to a ground control station, and then we use a synthetic aperture radar algorithm to retrieve a radar image of the subsurface. And in that radar image, we can detect the buried targets. The primary application we have been working at is the detection of buried threats, and in particular landmines and improvised explosive devices. And when we started working on this topic, our goal was to overcome limitations of similar systems for the same purpose. in terms of the ability of detect both metallic and non-metallic targets, speed, safety, because with a UAV we're always avoiding the contact with the soil, and resolution, as we are able to retrieve a radar image where we can obtain further information such as the shape of the targets. Moving now to the system description, all the prototypes share a similar architecture. We have 4 main subsystems. First, a flight controller subsystem and common positioning sensors on board drones, such as, for instance, barometer, inertial measurement units, a standard global navigation satellite system receiver, and so on. Then we have a communication subsystem. Even though the prototypes work fully autonomously, there's obviously the need of having a pilot in case of an emergency. So we have a data link for the pilot control. And then we have a data link to transmit all the measurements in real time to a ground control station. I haven't explicitly mentioned this before, but in order to retrieve high-resolution radar images, we need to know with very high accuracy the positioning of the UAV where each radar measurement was taken. And with very high accuracy, I'm referring to 1 centimeter, which for a UAV is not very easy to obtain. So in our case, most of the prototypes use a real-time kinematic sensor, which is a type of differential global navigation satellite system to have centimeter level accuracy, and also a laser rangefinder to estimate the height of the UAV from the soil surface. And then obviously we have the radio frequency subsystem, which is composed by a radar and a set of antennas. For us, obviously, the key components are the high accuracy positioning subsystem and the RF subsystem. So moving now to the methodology, I promise not to have questions, so I'm just going to explain a little bit how the processing pipeline operates. As a main takeaway, I would like to highlight that it's very, very important to carefully and extensively process the radar measurements. If we just take the measurement and apply a simple algorithm, it's not going to work because you need to take into account a lot of things. Our processing pipeline is mainly composed of 4 major blocks. First, we have an early preprocessing, which is applied to each measurement independently. So for instance, if we are using a noise radar, the first thing we need to do is to retrieve the impulse response. Then we have a preprocessing block, which is a set of different clutter mitigation techniques, where we mainly aim to remove the reflection from the air soil surface because it can completely hidden the reflection from the targets. Then we have the core block of the processing, which is a synthetic aperture radar algorithm, where we combine the radar measurements to retrieve the actual radar image, which looks like a heat map. And then we have a set of post-processing techniques to improve the quality of the image or to automatically detect targets. And on top of all this, additionally, we have a data subsampling strategy, because if for some reasons the UAV stops at a given point and takes a lot of measurements, we cannot process all those measurements as that would create artifacts in the radar image due to an oversampled area. So basically, with data subsampling, we decide which measurements are going to be processed and which measurements are going to be discarded. So now moving to the prototypes. These are basically the ones I showed you before. So at the beginning, we work with down-looking GPR architectures with 1 transmitter and 1 or 2 receivers. We got the contract from the Spanish MOD, and we improved the prototypes in both hardware and software. And for instance, we developed a prototype working at beyond visual line of sight operation. So that means that the pilot didn't need to be in contact with the drone, and also the ground control station could be far away. Then we explored a multi-static architecture with UAVs operating in synchronization. So basically, we had 1 UAV with the transmitter looking forward and another UAV with the receiver looking downwards. And with this kind of distributed architecture, the goal was to improve the detectability of targets placed close to the soil surface. This is an initial idea that I developed during my research stay at Northeastern, and we tested it in the framework of this project. And finally, we developed a multi-channel array-based architecture with 3 transmitters and 4 receivers. So in total, 12 different radio frequency channels, which enabled us to decrease the inspection time by a factor of 4, bringing it closer to real-time inspection. So now moving to the experimental validation. As you may imagine, we had to do a lot of experiments. Experiments are never easy. When you have to vary things within different types of materials, then it gets even more complicated. So at the beginning, we did a lot of experiments in the lab, and then we moved to experiments in the airfield of the University of Oviedo. And within the framework of the project with the Spanish MOD, we also conducted experiments in realistic conditions. Those experiments aimed to validate the technology with different types of soils and targets. So basically, regarding the soil, we consider different types of composition, soil surface roughness and moisture levels. And regarding the targets, again, different types of compositions, sizes, shapes, and depths. In most cases, we consider surrogates of actual devices. So we had a very close to reality experimentation. In the framework of the project with the Spanish MOD, we conducted 2 main experimental campaigns in completely blind conditions, which means we didn't know where the targets were buried, how many targets were buried, until we retrieved the detection maps. So it was a very good way to test the system in real in real life. Here, well, in total, we measured or we inspected 13 areas of 4.5 meters times 12 meters with different conditions. There were more than 160 targets buried, again, different types of targets. And as I mentioned before, it was a completely blind procedure. And here we can see one of those areas and the UAV inspecting that area. And well, I was also the pilot of the UAV. A lot of responsibility. And in this video, you can see the UAV inspecting one of these areas. Basically, it moves forward, then a little bit to the right, moves backward, and so on until it completes the full inspection of the area. I will show here, in particular, the results of the inspection of this section of a dirt road, where they had buried a low metal content anti-tank landmine, a couple of submunitions, an IED composed of a jack and a battery attached to it, and a wooden pressure plate. Obviously, during the experiment, the targets were buried. I'm just showing here the targets after they unburied them. With the combination of all the measurements, as I mentioned before, we retrieve a radar image, a 3D radar image, which looks like a heat map. Obviously, that's not very easy to analyze, especially when we are talking about areas of 60 square meters and then the depth. I'm showing here a section of this radar image in the main cuts around the detection of the jack, just as to give you an idea of how these images look like. So first, in the top view, we have the top face of the jack. In the along track view, in the direction of the UAV that the UAV was flying at, we have also, again, the top face of the jack. And more interestingly, if we look at the across track view, we can see also the reflection from the top face of the battery. And usually, it's very typical to have this kind of arrangements in the buried targets. So when you see this kind of shapes, you can infer a little bit what type of target is buried. Well, here you can see the last one a little bit closer. As it's not easy to analyze these 3D images, we built detection maps with sections of the radar image where we detect the targets. So here we have the portion of the radar image and then the coordinates of the detection and the depth. And as everything is georeferred with very high accuracy, if we have information from other sensors, we can overimpose everything together. In this case, we only had optical images of the scenario, and we overimposed our detection maps over those images. This is also quite interesting because in some cases, you can see a correlation between areas of the soil which seem a little bit different and areas of the radar image where you have detected targets. I mentioned before that it's very, very important to carefully process the measurements, and just to give you an idea of the importance, with an easy processing strategy, which is the results I'm showing here in the first column. Basically, you cannot detect the target as you take into account more details. you can not only detect the target, but also get rid of the air-soil interface, which is here, for instance, at Z equals 0, and at the end, it has almost disappeared. We have also tested the array-based prototype, which, as I mentioned before, enabled us to reduce the inspection time by a factor of 4. Again, well, this is one of the tests in a section of a dirt road. And in this case, the UAV also flies forward, then to the right, then backward, and so on. The difference is that here, the sweeps are separated 4 times the separation of the initial prototypes. And that's why we improved the inspection time. Again, we retrieved our detection maps. Here we had, again, a jack and a pressure plate. This was an anti-tank landmine, a plastic IED, a mortar grenade, which is very easy to detect in the radar images because the shape looks a little bit as the infinity shape. And again, looking at the transversal cut, for instance, in this area, we can also see the top face of a battery, which was also attached to the jack. And just going into the last works in this field, we have been exploring sparse sampling strategies to further decrease the inspection time. And we were able to achieve a reduction in the inspection time to just 10 minutes with a array-based prototype if we want a detailed inspection of an area of 60 square meters, and only 5 minutes if our goal is to detect medium to big size targets. And moving to the processing, as you may imagine, the processing of the measurements is quite time-consuming, especially taking into account that the measurements are gathered at arbitrarily sampled positions. And in order to overcome that, we have recently developed a strategy based on an efficient interpolation and a projection into a plane, which enable us to use FFT-based, well, fast Fourier transfer operations in the processing. And this enabled us to reduce the processing time from more than 24 hours when processing it in CPU with conventional algorithms to less than 20 seconds with this new approach. This brings me to the conclusions. These kind of systems are very useful to detect both plastic and metallic targets in a non-invasive way, faster and safer. We can also inspect difficult to access areas, and we can even retrieve images of the inspected area. Even though we have been focused on the detection of landmines and improvised explosive devices, obviously the technology can be used in other fields such as structural monitoring or archaeology. And as a main takeaway, in this blind experiment, we were able to achieve a high probability of detection, higher than 90%, for targets bigger than 10 centimeters, even in challenging conditions such as the ones we see in this video. I would like to acknowledge the different funding agencies of all this work, and thank you very much for the attention.
Very, very interesting talk. So, any question from the audience?
Maybe I missed something over here. When you detect the mice and the were unvaried or fully varied?
Fully varied. Yeah, so basically, well, experts from the Spanish MOD buried the targets. We did the experiments, and then after we finished the experiments, they unburied the targets and took the pictures. And then after that, after we retrieved the maps, they told us, okay, you have here the pictures and the coordinates. Yeah. No, actually, most, like, I would say maybe 90% of the consumption is the UAV itself. We use the same batteries to power up the radar, but the consumption is nothing compared to the UAV. Our limitation, for instance, for the inspection time was the UAV flight, because obviously we are not experts in drones. We had to work with them, but the radar didn't consume much. So basically, in the last prototypes, we were using a noise radar working from 600 megahertz up to 6 gigahertz. The thing is that after 3 gigahertz, unless you are working with very dry sandy soils, you don't get much penetration into the soil. So we don't usually process that information because it just adds processing time and not very. It depends on many things, especially the conditions of the soil. In wet soils, the detection capabilities get significantly worse. In most cases, we have been operating up to 30 centimeters, because for this kind of applications, most of the targets are very close to the soil surface. You're welcome.
So, any other question? We have another one from online, but Pierluigi?
Yep.
Okay,
Hello, I'm
you can go.
Pierluigi. I'm Pierluigi Valorni from the University of Florence.
Thank you.
I would like to understand if you have performed some kind of validation. So, for example, using rock curves, the receiver operating curves that are very useful to understand the relation between false alarms and correct detections. Did you?
Yeah. I only mentioned here the final figure of the probability of detection we achieved in the last tests. But yes, as you may imagine, and probably that's why your question is coming from, one of the problems of radar systems in general is that usually the false alarm rate is a little bit high. For the experiments I show at the end with the blind experiments, the false alarm rate we achieved was around 23%, if I remember right. So, well, we did that kind of analysis.
Okay. And second question is about the burial procedure. How many times passed between the burial of the objects into the ground and the measurements?
It depends on the scenario. So some of the experiments are done without just without much time between the burying of the targets and the experiments. But the ones that I show here, there was, well, some of the scenarios had the targets for several weeks. Obviously, it would be better to have them for longer, but that's what we could have.
Okay. Okay.
It's not
Thank
very
you.
good to do the experiments very recently, because it may give you a detection which is the detection of the hole that you ticked rather than the target. So
Yeah.
obviously
You don't have roots, you don't have water flooding and other clutter scenarios and so on. Okay, but I understand the difficulties. Never mind.
well, we had experiments with water around. Yeah, but that's tough.
Okay, understand. Thank you.
Thank you.
So, okay, last question, Miguel.
You can ask me later.
As you want. Okay, so thank you very much, Maria. Te escucho bien, Mario.
So can you hear me?
Yo no tengo...
Okay.
¿Se escucha bien, Mario? Sí, ¿no?
Esto no estoy preparado yo para la tele.
So let's pass to the third talk of this morning. So now we have the presence of Miguel Beruete. He comes from Universidad Pública de Navarra, Public University
Very good.
of Navarra, and he will talk about smart metasurfaces and advanced wireless communications in the millimeter wave band.
Yeah, many words here.
So
yeah.
Miguel.
So thank you very much for this kind invitation to be in this seminar. I kind of remember that we were together in Philly in a bar when we discussed about this with Antonio, and it's a great opportunity. I think it's a good initiative so that we can show different aspects of research. I'm going to show you here something different from the previous talks, so it's a kind of varied. That's nice. In my case, I'm going to give you an overview of the things that we are doing, okay? Most of the things in this group you already know, but in any case, I think it could be interesting to see another viewpoint, okay, of the things we can do. So several keywords, millimeter waves. Yes, I guess all of you know what this is. In any case, I will explain something in case someone doesn't know so much about this technology. And in particular, smart metasurfaces. So the main idea, well, I took these images from AI. So but it's nice, it's like how can future systems look like? And one of the things that are being proposed in technology in 6G, 5G, 5G, 6G, and evolutions of that is to have everything distributed in the walls. They are speaking of smart walls, okay? And that's a very provoking idea, and that's very attractive idea. So instead of having routers which are localized, imagine that your wall has something on top, like a coating that you put, which is intelligent enough so that it can interact with the radio system, and that could be great. And in this respect, metasurfaces are going to be instrumental for that, because metasurfaces are exactly that. Are things that are really thin that you can design so that they have some response, and then you can integrate in if you add active elements, for instance, you can integrate in the radio system. And with that, we could have like dynamic beamforming. It could be static or dynamic if you have intelligence for that. So that, for instance, you could follow a user and give this user a dedicated beam, and then all the resources will be for this user, and that's great. As you move around, all the resources are for you, and because you are, for instance, downloading high quality video, something like that. Or you could have then with this more energy efficient systems or signal optimization, you can understand this. And also integration that with IoT in general, they're speaking of having routers, distributed over the walls. And you could also have security and privacy, so that the metasurface is able to block the communications where they shouldn't reach, or even include some cryptography so that only the user, which the key, can interpret the communication. And in this regard, well, millimeter waves are going to also be instrumental, because now we are in the tendency that we are always demanding more and more and more from the communication systems. When I was a student, it was just the beginning of the mobile communications in Spain. And we were really satisfied to be able to send SMS, those messages that you even had to pay for them. So we had to invent ways of spelling, to make it them understandable, but not many letters like in a telegraph, for instance. But now that should be, of course, is not enough, and people want to have real-time, high-definition video, and so on and so forth. So we are moving from megabits to gigabits per second, and they are also speaking of terabits per second, which will be crazy. Okay. In this regard, we need much more bandwidth, and in order to get that, a very simple way is just to move the frequency upwards. So instead of working in microwaves, let's work in millimeter waves, and automatically we are going to have more capacity. That's why now many initiatives, and these are being proposed even by operators and manufacturers of equipment, they are putting a lot of effort on millimeter waves. Okay, and in this regard, metasurfaces are going to be instrumental, as I said at the beginning. Here I'm going to distinguish into two types of metasurfaces, okay? Static designs, which are the simplest designs. Once you design them, you don't change them. But of course, it's much more attractive to have these, like reconfigurable devices. But in order to understand reconfigurable, it's good to understand static devices. And let's not neglect, let's not diminish the power of these devices, because we could do many things just playing with the metasurface itself. For instance, you can have different response for different angles, for different polarizations. You can create different vortex beams. You can have the different beamforming depending on the frequency. So this is kind of interesting. And indeed, you could put the metasurface, only the metasurface on the wall, and then have some intelligence beyond the metasurface, okay? So that with different beams, you can have different response, and just you centralize all the intelligence in a single device, and then the wall is just passive, but it's doing some magic to the wave, okay? But in any case, this could be like the final goal, reconfigurable devices. And as far as I know, in this group, you are doing many things, many interesting things on this. So you already know how it was. I mean, you can have this with some intelligence, and then it can, for instance, steer the beam in different directions. And then we could reach this thing, which the Americans call wireless on wall, which is nice because they call them WOW. They are the masters of marketing. I also like to call them smart walls because this is probably the main, a good definition of what they are going to be. And in this regard, I had the luck to be with a Fulbright grant in New York under Andrea Alu's supervision this year. And the idea there was to do this with space-time metasurfaces. So it was like, just generalizing everything and putting the variable time, okay? And with that, you can have modulation, you can have many other things, you can have non-reciprocity, you can have full duplex communications, you can have many things. Indeed, we didn't have the time, sorry. So you will see that what I'm going to show you here is not about that. And the question is that this is difficult to do, okay? And the reasons are here, These designs, if you are doing something, and you are doing something here, by the way, you are doing them in microwaves, maybe in Ka band, but this is still microwaves, almost in millimeter waves, but it's not still millimeter waves. The question is that doing this in millimeter waves is going to be difficult because we don't have the elements, we don't have the devices, we don't have the lampet elements, we don't have pin diodes, we don't have varactors, we don't have things that are working well in the millimeter wave band. So that's why most of the designs are in microwaves, and this is challenging to do in microwaves. It's even more challenging to do it in the millimeter waves. So, let's keep this as the end that we want to target, okay? But now what I'm going to show you is the things that we did before towards this aim, okay? So this is the idea. I'm going to tell you about holographic metasurfaces, and I think it's a very nice concept because this is just the basis of everything. So how can we play with the waves in a metasurface? Well, the idea is to apply these holography principles, which is as simple as this. You just pixelate the metasurface, you just pixelate the surface in general. Here are just colors, just to make this understandable. So each color is going to represent a different phase. And now if you are able to implement these phases, just playing with the phase, and this is the key concept, the gradient of phase or the phase gradient, then you are going to be able to have any response you like, which is nice. So the most simple response is just beam steering. This is linear phase increment. You can have parabolic phase, which is going to give you a lens. You can have much more crazy ideas like these kind of phases where you get images. This is holography, properly speaking. Of course, for communications, having images is not so important, but I mean, it just gives you the idea of the potential of this simple idea. Just play with the phase, get anything you like, okay? So how can we do this? How can we modulate the phase? Well, as far as I know, and correct me if I'm wrong, I know two main techniques, okay? The first one is let's implement different elements so that each element is able to give me a different phase. Or another very provoking concept is let's play with the same element, but let's rotate it, and then with this rotation, we obtain different phase. This is called geometrical phase, and it needs several very particular conditions. I will tell you with some very simple equations how this works, okay? So let's start with this one. My main topic is going to be about this, but I want to give you some overview of this. So these are two examples that we did in the past, okay? This is the first one. This is what we call a reflector array metamirror. And you can see clearly that here we did what we call morphing of the elements. So we are changing from this small square towards a bigger square, and then this U-shaped resonator and this C-shaped resonator. And here you see, we have all this phase Gaussian covering with 360 degrees, and then the reflection coefficient magnitude, well, it should be always near 1. Well, there are some resonances, it goes below 1, but in general, it has high reflection, okay?
And then, in order to have, in our case, we wanted to have a one-spot focusing and four-spot focusing, like you see here. So this is the phase that you calculate. This is working in reflection with some incidence angles. So that's why you see here ellipsoids instead of circumferences. And this is the other case. This is calculated with an imaging algorithm. This is called a Gerber-Saxton algorithm. And the idea is very simple. You just take, for instance, this phase distribution, you pixelate it, and then you find which element is going to give you the phase you need in each pixel. And then you just, just pick the element and put it here, there. And these are the experimental results. I call your attention about this. This is done at 350 gigas. This is, high frequency. This was difficult to do. And you see that clearly we get the one spot and here the four spots. And this is nice animation where we see the frequency response of this structure. You see that this is designed at 350. When we reach that frequency, we have the maximum, and then it decays. So 360 maybe. I'm not sure now about the exact frequency, but you see that this kind of narrow band, and this is going to be characteristic of this methodology. If you use different elements, you usually are going to have this response only in a limited number of frequencies. This is going to be narrow band. Another idea, which was kind of, appealing at the time, is the invisibility cloak. This is a type of carpet cloak. The idea is that you have a ground plane and then you have the incidence and reflection. Then you put an object, and of course you have some scattering, and this scattering is going to make this object detectable. And then if you want to make this invisible, then you can cover this with a metasurface, and then you more or less retrieve the initial situation. In our case, this metasurface is done with different elements. It's like two coaxial rings on silicon, on metal. And here again, you see that the phase goes through all the values, and the response, the magnitude of the response is more or less equal to 1. Here, well, the more details, we need to do this at two different angles, 25 and 65, because we have these two surfaces, 25 and 65. In any case, this is how the design works. And the only thing that we are doing here is just to change the radius of the rings. Okay, this is the radius, and this is the incidence angle. In any case, here are simulation experimental results. Incidence at 45 degrees, so the reflection is at 135. This is specular reflection. With the bump, there is a lot of scattering around, and then when we close the bump, you see that the scattering is very much reduced. Okay, and this is making this object almost invisible. This was done at 87 gigas. This is again millimeter waves, so that's why we are always working on this. Okay, and now moving on to the other technique, the geometrical phase. Okay, I'm going to put this simple. So we need several conditions for having this. First one, we need to have like a polarizing device. Okay, called half-wave plate. Half-wave plate is the polarizing device which is able to convert the handedness of circular polarization from left to right or vice versa. Okay, in linear components, in linear polarization components, this is equivalent to having 130 degrees of phase difference between, for instance, X and Y component. Okay, with this you are going to have the half-wave plate that you want. So now, if you under rotation, well, this is the Jones matrix of the element. Under rotation, this is the new Jones matrix. We have multiplied by the rotation matrix, and we have this relation. So the important thing now, if I have this element rotated and then I impinge with circular polarization, we obtain something very interesting at the output. First thing, we see that the sign of the J changes, so it goes from left to right or right to left. This is what we expected. But in addition to this, we have something which is very interesting. We have this new element, which is a phase, which just stems out of the rotation of the element. So the phase that you obtain is 2 times the rotation angle. So this is very simple. Just design the element and then rotate it, and you have the phase. And that's it, simple. Just you can implement, again, any function that you want. That's so great. So, this has been done in the past, in optics, for instance. These are the works by Capasso in optics. Many results. Dielectric, the resonators in this case, not resonators, only dielectric elements, okay? But, this works very well in optics. But if we go to millimeter waves, to microwaves, we have better ways to do this. And indeed, what we usually do is to use metal or dielectric elements. So with metals, okay? See, these are some examples that we found in the literature. They are quite nice. As you can see, they are 3-layer devices, 3 layers of metals. And if you have experience on this is a problem, because you need to have a very good alignment between the elements. Otherwise, this is not going to work very well. And aligning, in a single dielectric layer, two metallic layers, that's difficult, but that can be done easily, more or less, okay? Now that we have the techniques, if the dielectric is transparent, for instance, you can do it with some accuracy. But then if you need another additional metal layer, you need to align this new metal layer without leaving air gaps, having everything very, very well aligned. And that's difficult. So, this was nice. They're able to do this with good accuracy. Indeed, they have this vortex pin, they have a lens. But our challenge was, okay, can we reduce the number of layers? Ideally, we should go to one, but you can demonstrate that with one layer, you don't have efficiency. So the minimum is 2 layers. And this is what we did. We took this simple resonator. This is an H-shaped resonator. There are 2 identical H-shaped resonators on top of each other. And here you can see with this, we wanted to do a lens, a meta lens at this frequency, 87 gigas with this focal length. This is just our design constraints. And here is the ideal phase and the implemented phase. And you see they are almost indistinguishable because, of course, with this methodology, it's very simple to just get the phase. It's just rotate the elements and you will have it. And here is a demonstration that this is working as a halfway plate. We have left-handed at the input, and then we have right-handed at the output. This is the transmission from left to right, okay? And when we rotate the elements, the magnitude is almost the same, but the phase clearly changes because this is what we expect. This is, then in agreement with the geometrical phase constraint. Okay, so to just make the story short, we did the measurements, and then here you see that indeed we have a focus. This is the horizontal plane, this is the vertical plane, and this is the front plane. And we clearly see that we are creating this focus. This is working quite nicely. And in our aim towards proposing this for communication systems, we decided to do the experiment by putting here a horn antenna, the focus of the lens, and then the lens, and just evaluate how the radiation pattern is changing. And clearly, the antenna has this, let's say, broad beam, okay? When we put the lens, it's much narrower. And this translates into an increase of the directivity from 17 to 34, okay? So this lens is doing its job very well. It's going to increase the directivity. It's going to only focus in one direction, increasing the directivity in the other direction. Okay. So, I was telling at the beginning, with the static metasurfaces, you can do many things. And this is one of the latest results that we have. Indeed, this is not published yet. This is called full space metasurface. And the idea is to extend the reach of metasurfaces by playing with different regimes, frequencies, I don't know, just functionalities, whatever you want. So in our case, the idea is let's stick to 2 different frequencies, like around 50 gigas and 104 gigas. And then, for instance, in the low frequency, we are going to work in reflection, and we are going to implement the functionality, the simplest one, just beam steering. But in transmission, we are going to do something more sophisticated. We are going to, in high frequency transmission, and we are going to do an hologram, okay? So first thing that we need is to add complexity to the unit cell, because now we need to work at different frequencies. So as you see, we base the results on the H-shaped resonators, but now we are adding these split ring resonators at the input and at the output around this H-shaped resonator. And on top of that, we need this middle layer. This is crucial. This is very important, because this one is going to act as a ground plane for the reflection regime, a low frequency, and it's going to act as a transparent element for the transmission regime, because we need coupling from the input to the output. So the slots must allow the field lines to couple from the input to the output. Of course, this has a lot of optimization, but in any case, we were able to reach this. And it's very nice because now we have different knobs that we can touch to control the transmission in each frequency regime. For instance, if I rotate the ring here, you see that the transmission doesn't notice. It's just the same. It doesn't matter if I'm rotating the ring. But in the reflection, clearly, the magnitude is the same, but the phase is changing. And the change of phase is twice the rotation angle. This is Bachelor number phase. Conversely, if I rotate the H-shaped resonator, the reflection doesn't feel anything, but then in the transmission, I have this phase change, which is Bachelor number again. Indeed, if we go to the full analysis, we are rotating both elements in all the possible angles. This is beta, this is alpha for the ring and for the H resonator. And ideally, if I rotate this guy at low frequencies should fill all the phase states. And this is what happens in the simulations. But there is no change if I rotate alpha. If I rotate this, no change. And this is also what happens in our simulations. And the other way around, rotating this, I only see here and no change in this direction. And the same happens in the simulations. So we have independent control on the response in each frequency region. Now we can implement any functionality that we like. And this is, for instance, as I mentioned at the beginning, beam steering, which is analytical. It was nice because we could do it easily. We impose 20 degrees at this operation frequency, and in the simulations, we get this 20 degrees as expected with a very nice accuracy. In transmission, we do the hologram. I save many details here. It's an imaging algorithm and so on, several optimizations. Here is the Huygens-Fresnel analysis. We use this because this is an analytical method and it saves a lot of time in our simulations, and it has a very good accuracy with the simulator. This is CST simulation, and you can see that clearly we define the same shape, and this is the experimental measurements which are working quite well. So, and this is just a nice animation with the Huygens-Fresnel analysis where we see that an hologram in the end is like a very complex lens. There is focusing, and then there is defocusing when you go away from the focal distance, which was 20 millimeters in this case. Okay. So this is about the static designs. Now I would like to move forward towards the only result that we have for the moment on dynamic or reconfigurable devices is a liquid crystal reflect array. Indeed, for reconfigurability, this is just an overview of the things that you can use. Probably there are more, but these are the ones that I found. You could use MEMS, pin diodes, varactors, graphene. For graphene, I didn't find experimental results for the moment. Maybe it's my mistake, but I couldn't find many about them. In any case, all these devices work very well. But again, in the microwave regime, okay? If you want to move forward to scale to the millimeter waves, then you are going to have some problems because there are not many manufacturers giving you those devices. So a possible replacement, a possible alternative is using liquid crystal. Okay, so for those of you who don't know about this, let me just explain you the basics of this. Liquid crystals it's a state of matter where it's neither liquid nor solid. It's characterized electromagnetically by these ellipsoidal molecules. These are uniaxial materials. So in principle, we have this permittivity tensor. And then the interesting thing of these materials is that you can rotate the molecules with some biasing voltage. So for instance, if we have this situation here, and for this electric field here, then in this position, we are going to see this permittivity, the perpendicular permittivity, okay? Now if we include some biasing, we rotate the molecules, and then in this situation, we have the parallel permittivity. And in the middle, we will have something in the middle, okay? So we can have a material whose permittivity is changing under the application of this biasing. And this is going to be what we are going to exploit for the control of the response. I call your attention also on this. Typically, we have a small contrast between these two permittivities. So in principle, this is promising, but we have to do something if we want to exploit this in millimeter waves. Let me explain you why. In principle, if I want to exploit this, the liquid crystal to get some phase difference between one permittivity and the other permittivity under the same polarization, the contrast is going to be small. And this is added to the fact that the thickness of the liquid crystal is going to be around, let's say, 40 microns for millimeter wave wavelength. This is going to be a strong limitation because if I have the wave propagating, of course, there's going to be some phase difference, but not too strong. So how can, even though I switch the states in the liquid crystal, the phase difference is going to be very, very weak. So in order to increase that, we need to work near a resonance. In a resonance, you have this characteristic phase response. So now, if I change the permittivity, this resonance is going to move, okay? And then I'm going to have a strong phase difference I go fast, okay. Strong phase difference, sorry, I speak so much. Okay, so resonance is critical, okay? So let's go. the design is simple. It's just ground plane, liquid crystal, and patches here. This is the biasing lines connecting the patches. Long story short, this is the reflection coefficient as we change the rotation of the molecules. In the magnitude is, there are some losses, minus 2 dB, not very big losses. This is one of the best liquid crystals that you can find. And in the phase escalation, 266. It's not 360, but still reasonable, okay? So simulation results, here you see that we are able to move the beam by changing, the polarization of each unit cell. So we are moving the beam. First thing that we notice is that the bandwidth is quite narrow. This was expected because this is working in resonance, okay? So moving to the experiments, here you see things are much worse. And let me explain this, just give me 1 minute to explain this. Because I think it's important if you want to work with liquid crystals. This is a strong limitation that we found. In principle, here we see that this is continuous, but here is like, stepped, okay? And it's much more clear in the phase. There's a big phase gap. The reason for this, we think, is that the molecules for this liquid crystal are kind of long because they must be working in millimeter waves. So they have a lot of inertia. So if I want to move them, gradually from one state to the other, this is ideally what it should do. It should go gradually, but in the end, it's like I'm staying here and suddenly I change. So I have a gap here, and this is going to be very, very detrimental for the operation of the device, because you can see here now in the experiments, please, I need all your faith to believe what I'm going to say. I'm saying here that we're moving the beam, but in principle, what you see here is that most of the radiation is always at 20 degrees, specular reflection. And here, well, you can see that there are some bands where, yes, we are steering the beam, but this is not perfect. We know, we are aware of this, that this should be, improved. I'm not going to tell you the story about this. If you want, I could in the questions or maybe during the lunch. But indeed, we wanted to repeat this. We couldn't. Okay, so now we are working in different prototypes. And this leads me to the conclusions. These are my conclusions. You can do many things with metasurfaces at millimeter waves, and this could be exploited in communications. Full stop. Thank you very much.
So thank you very much, Miguel. Very, very interesting, because you say that Americans are master of marketing, but you talk very, very nice.
I've been 6 months in America.
About metasurfaces. So very, very nice introduction about metasurfaces. So any question from the audience and from people who is online?
No questions. I was so clear.
No one? I have some questions.
Okay, good.
But I have everyone is going to laugh, but I have a curiosity. When you were talking about the prototype in reflection and transmission,
oh yeah,
you know, no?
Yeah, this is one, the full space, this one.
About holograms, we will talk later. Okay.
Okay.
But this one, yeah, I was wondering if you can show the cell, please.
Oh yeah.
This one. Okay, so you have so the dog bone and the split ring, they are patches. No?
Yeah, they are patches, yeah.
But each of them control each of the band. Am I wrong?
Yes, yeah, no, that's completely true. The rings control the reflection here, and these H-shaped resonators the transmission here.
So my question is, what is the role of the medium layer? Because the H and the ring, when they resonate, usually you have reflection. No? So if you are controlling both bands with the same with patches, how can you invoke transmission?
Yeah. Good question. I was too fast in this. Yeah, I was feeling nervous to finish. I had so many things to say. So yeah, in principle, this guy here is going to act as a ground plane for the low frequency band, more or less. And you can see that it doesn't. The response doesn't change so much if you put just a ground plane here, and it's tuned in order to have the slots so that they don't block the electric field lines that are going to connect the inner the output layers, the inner and output layers, so that because indeed for the transmission this is based on this design here, and there we analyze how the F-shaped resonators are working. So there are some resonances for one of the polarization, I mean for linear polarization. For the other polarization there is magnetic coupling, so that it's like you need to let them connect together. That's why. So the ring is not resonating, or
Okay.
let's say, it's just it's acting as a passband filter, something like that.
Okay, so you have sort of passband filter,
Somehow.
but as a combination of all the cell, including both patches and,
Yes. Yeah.
and the slots. Okay, very nice, very interesting.
Thank
Very
you.
interesting. So, any other one?
So shy. No problem.
Okay, so thank you very much, Miguel.
Thank you.
Sí, creo que la tiene. ¿Verdad? Al revés, ¿no? Mm. Sí, sí, ok. Quitar gain, ¿no? Okay, so thank you very much, Mario, for coming and for being on disposal to present a work here. So next speaker is Professor Mário Silveirinha. He comes from Instituto Técnico Lisbon, it's like that. And he will present a work called chiral gain photonics. So Mario, please.
I think it's not in, okay. Okay, no, it's fine. Okay, good morning, everyone. So first of all, I want to thank Antonio and Carlos for inviting me to participate in this event. And I'm going to discuss chiral gain photonics as indicated by my title, but first of all, a little bit of motivation. And as you know, electronics and photonics, usually they are regarded as different fields. Electronics, people deal with voltages, currents, circuits like transistors and so on. And in photonics, we deal with waves, polarization, interference phenomena, and so on. However, it would be very interesting to bring some functionalities from electronics to photonics. For example, perhaps the most important component in electronics, it's the transistor, and it allows you to isolate parts of a circuit, or for example, to amplify a signal. And we don't have the same versatility in photonics. And motivated by this, some years ago, we asked the question, can we engineer a transistor-like response for waves? So as you know, a transistor, essentially, it's a point-type device, dimensions much less than the wavelength. The idea is to have the same functionality in a material that can be several wavelengths. And I'm going to start by discussing the solution that we proposed, and then building on that, we'll see the chiral gain, which is the topic of the talk. Okay, so the solution that we proposed is inspired by the operation of this well-known MOSFET transistor. It's a simple device. There are 3 ports, source, drain, and the gate. Essentially, this is a resistance. So this is a conductive channel. And the important point in a transistor is that by acting on the gate with the voltage, you can control the width of the channel, and so you can control the resistance of the channel. So, of course, the channel is, the transistor is a nonlinear device because the resistance or the conductivity, which is the inverse, they depend on the voltage on the gate, which is the same as the electric field along the vertical direction, okay? So one important point is that we are controlling the response along X, the conductivity along X, by acting with the field along Z. So the question we ask, what would be the metamaterial analog of this device, which, as I explained, is essentially a point-type device. And so this is like what we envision, like a set of transistors, a periodic structure of transistors. Later in the talk, I'll show you more realistic things that you can use to imitate the operation of transistors. And if we want to imitate what I just described, we would like to control the material response along X by acting with the field along Z. So it should look like this. So of course, if you have material, the response is usually anisotropic, so it can depend on the orientation of the applied field. So it's a matrix. And here what we want to do, as I just mentioned, control the response along X, which is this element, by acting on the field along Z. So this is the analog of a transistor, but for waves, okay? And I'm going indeed to show you with more details that it has some functionalities, same functionalities as transistors. So suppose that we have this, it's a nonlinear material similar to transistors. How can we use it? So the way we propose to use it is in the same manner that typically we use transistors. So usually we bias them with, in the case of transistors, by applying a voltage across the drain to source direction. And with this, we fix a point of operation, okay? And we are going to work around this point of operation. And now, provided the perturbations around the point of operation are weak, the response can be linearized, and so essentially it becomes a linear device. For example, this is how we make amplifiers, right? So we choose the point of operation, and then you just find the response around this point. So if we do the same for the metamaterial, it's the same as saying that we bias the metamaterial with a static electric field. You'll see more details about this later on. And so you have the static response, and then you have the linearized response, which is basically the dynamical part of the response. For example, now you apply a microwave or a terahertz signal on the top of this DC bias. And what we find by linearizing everything, it's just Taylor series, nothing more. What we find is that the linearized permittivity looks like this. So this relates the dynamical electric field with the dynamic displacement vector. And looking at this permittivity, by the way, for our simple model, toy model, if you want to call it, all these numbers are real valued. And you can see the structure of this epsilon is very different from the usual structure that we find in normal materials. Namely, the most striking aspect is the fact that we have this element here that is non-zero, but on the other hand, the opposite symmetric is 0. So this matrix is not symmetric, which, as you may know, implies that this material will be non-reciprocal. And furthermore, this material is non-Hermitian, which means that if you transpose and conjugate, you don't get the same result. It's non-Hermitian, which means that there can be either gain or dissipation effects involved. And in fact, I told you this should look like transistor, so we expect gain, and indeed we are going to have gain. I'm going to show you that it's a special type of gain, this chiral gain that was the title of the talk. Okay, so this is what I want to show now, that indeed this gain is a special type of gain. And before I enter into the chiral gain, I want to look at, again, at the generic material that has an electric response described by some permittivity, okay? And let's suppose first that we have a conservative system. So like a standard material, not standard because usually they have loss, but some system that for all practical purposes, we can neglect dissipation. And so in that case, the permittivity should be a transpose symmetric tensor. So it should be Hermitian. So being Hermitian has one important property. The eigenvalues of this tensor are real valued. And what I want to highlight here is the importance of the sign of the eigenvalues, okay, for a conservative system. So the first case is, let's suppose that all the eigenvalues are positive. This is like similar to a conventional dielectric. And in this case, if you look at the isofrequency contours, which basically are the surfaces in momentum space for a fixed frequency, well, they look like this, like ellipsoids. So in this case, it's like a dielectric type response, okay? So another interesting case is when you have all the eigenvalues negative. This corresponds to a tensor that is negative definite. Actually, I wanted to discuss this one first. And in this case, if all the eigenvalues are negative, it's like a metal type response. So you have a band gap. No propagation is allowed in the material. And the last case is when you have an indefinite tensor, so some eigenvalues are positive, the other ones are negative. In this case, as you know, you get different type of isofrequency surfaces, namely they are hyperbolic. And these hyperbolic metamaterials have indeed, in the last 10, 15 years, caught the attention because they have many applications. I don't want to discuss that now. So here the important point is that the sign of the eigenvalues of the conservative part of the response has a huge impact in terms of the physics of the wave phenomena, okay? Now I would like to discuss the non-emission response. So realistic materials, they always have some dissipation, some loss. And in that case, it's useful to decompose the response of the material into a conservative part, defined like this, that I already discussed, essentially is what I discussed previously, and the non-conservative part, which is defined like this. You can notice that they are combined with the imaginary unit as shown here. So one important point is this epsilon 2 primes, which is the non-conservative part, is also an emission matrix. So all the eigenvalues are real valued. So first of all, what is the meaning of this epsilon 2 primes? So the simplest way to see the meaning of this is to look at the power that is dissipated in the material. So the power dissipated in the material, let's call it Q, is written in terms of a quadratic form that involves this epsilon 2 primes multiplied by the electric field. So if you have, so this is the power that is transferred from the wave to the material. So if you have a regular passive material, a dissipative material, we know that there is always dissipation. The energy is always transferred from the wave to the material on average in time harmonic regime. And so you have attenuation and so on. And this implies that this epsilon 2 primes must be a positive matrix. All the eigenvalues are positive. Now, this is what we have typically. Now, if you have systems with gain and typical systems with gain, well, we should have gain for all polarizations. And so it should be kind of the opposite of this. So in systems with gain, the material can supply energy to the wave. You can have amplification. And in this case, epsilon should be negative. Okay, all the eigenvalues negative. Now, the interesting case I want to discuss, it's something in between. It's if you have a matrix that is indefinite, which means some eigenvalue is positive, some eigenvalue is negative. In this case, the material is not dissipative, is also not a standard gain material. Actually, you can have both at the same time. How can this be? Well, both at the same time, because there is polarization. And so for a particular polarization, the material will act as a dissipative material, just absorb the energy. For another polarization, it's going to amplify the wave. Okay, so you have a mix of the two things. And this is what we call an indefinite gain material. So you can have both situations. And furthermore, I'm going to show you next that this transistor metamaterial is even more special because the polarization that activates the loss, it's a circular polarization, and the polarization that activates the gain is also a circular polarization, but with the opposite endness. Okay, so this will be a chiral gain material. So this is what I'm going to show you next. So I go back to the MOSFET metamaterial that I discussed in the beginning, and I look at the non-emission part of the response defined as shown here, as I discussed before. So it's this tensor, and we can easily find the eigenvalues to see that indeed there are some eigenvalues positive, some eigenvalues negative. Well, here they are. You have eigenvalues with both signs. They are controlled by this interesting parameter that I mentioned previously that usually is not there alone. And so indeed, this material can provide gain and loss. And these are the corresponding eigenvectors, which have the meaning are the polarizations that activate either gain or loss. And in this case, as you can see, they are polarizations in the XOZ plane. Basically, it's the plane of the drain to source direction and of the gate, if you want to go back to the microscopic structure of our transistor metamaterial. They are circularly polarized, and the endnesses are opposite. So it's depicted here. If you have a wave that rotates like this, it activates dissipation in the material. If you have a wave that rotates in the opposite direction, it activates amplification in the material. Okay? And so the response is chiral. The gain response is chiral. Now, we can say a little bit more. For this particular type of structure that we have Well, our tensor is antisymmetric, and I don't want to lose time with mathematical details, but this means that we can always write this non-emission part of the response in terms of a vector, a pseudo vector. Let's call it omega. I call it the gain vector, so it can be written as you show here. So if you plug this formula, so as I told you, epsilon 2 primes controls the dissipated power, okay? And if I plug this formula into the form of the dissipated power, and if we manipulate and massage things a little bit, we find that the dissipated power can be written like this, okay? And now the interesting coefficient is the one in red. And the one in red is controlled by this gain vector, which is directed along y, by the way, in our problem. And is controlled also by this quantity that is the spin angular momentum of the wave. The spin angular momentum of the wave is intrinsically related with the concept of polarization. Namely, if you have a wave, you can look at the polarization curve, and if it's not linear, it's going to be rotating in some direction, in some plane. And so the spin angular momentum is perpendicular to the plane of the polarization, the plane of the electric field, and the direction is controlled by the endiness, okay? So what does this formula tells us? Tells us that the sign of Q is controlled by the relative orientation of this omega, which is fixed, just depends on the material, and of the spin angular momentum of the wave, the polarization. So if you have a wave with a spin angular momentum aligned with the gain vector, then you are going, this Q is negative, which means that you have gain. The dissipated power is negative, so you have gain. On the other hand, if they are anti-parallel, in that case, you have dissipation, okay? So what activates loss and gain is this spin angular momentum. So there is a strict link between the non-emission effects, gain and loss, and the spin of the wave, which is a quite unique thing, and I'm going to explore this further. Okay, so to gain some insights, let's look at the wave propagation in this metamaterial. And let's start with the simplest type of problem, a plane wave propagating in the material along some direction, some wave vector k, and of course, this is controlled by the Maxwell's equations, as usual. We are going to fix a particular direction of propagation, specifically the direction of the gain vector, omega. So it's going to be propagation along y, to fix the electric field in the XOZ plane, which is the plane where the eigenpolarizations that activate gain and loss live, okay? And now we look at the plane waves. So based on everything that I explained you, maybe you expect to see waves being amplified or waves being attenuated. It is not like that. Actually, if you do the calculation, you find that there is a wave that has this wave vector for a real valued frequency. So it's not different from the usual stuff. And there is another wave that is this also real valued wave vector. So we don't see the gain directly. Why we don't see the gain directly? Well, it turns out that the polarizations of the plane waves are linear polarizations, as normal in a standard dielectric material. You see them here. And because they are linear, they don't have a spin angular momentum. You just have spin angular momentum if you have elliptical or circular polarization. And so they cannot activate gain or loss because there is no spin. On the other hand, you can notice one interesting aspect is that for a normal material, these two vectors should be perpendicular. So this theta angle should be 0. But because we have this transistor response, we always have this interesting angle, theta, which is defined by this formula. And so the two waves, the two electric fields, they are not perpendicular to each other. This is a property that follows from the fact that the response is non-emission. Okay, so we cannot get gain if we just have plane wave, a single plane wave propagating, like illustrated here. But what about if we consider a superposition of the two? If you consider a superposition of the two, why is this interesting? Because you can control phases. And so if you control phases, you can locally engineer a polarization that is nonlinear. It's just combining two different waves with different phases. So let's see what happens in this case. So you superimpose the extraordinary and the ordinary waves. And we are going to look at the pointing vector associated with this superposition of two plane waves in the material. Okay, so we look at S, the pointing vector, and what you should expect. Well, if it's a normal material, a standard material, and there is no loss, the Poynting vector of a superposition of two plane waves, or three, if there are three at the same time, or four, or whatever, they are all independent. And so the Poynting vector for plane waves always combines like this for any conventional material, okay? And so you expect to see a constant Poynting vector. The flux of energy is constant through the material. If it's not constant, means that you have non-emission effects. Now, in this case, because in our metamaterial, I'm sorry for this problem with the fonts. So in our metamaterial, it's a non-emission material. And so it's not constrained by this property. And in fact, you find that the Poynting vector has three components. You have the Poynting vector of one of the waves, the extraordinary wave, the Poynting vector of the second wave, the ordinary wave, and then you have an interference term where the electric and magnetic fields of the two waves, they mix with each other, as shown in the formula. Now, because the two waves have different propagation constants, one is, let's say, K ordinary and the other one K extraordinary, when you mix them, the propagation factors don't cancel out. And in fact, you have a variation in space like this that is controlled by the difference of the propagation constants. So the Poynting vector is not going to be constant. This term is constant, but this term varies in space as a cosine. And I show you this in an example. So this is a metamaterial with these parameters that I show you here. And this is a wave propagating along the y direction. And this is the Poynting vector as a function of the propagation distance. And the wave is a superposition of two waves, as I explained. And so you see you have this power beating that I discussed previously, and you see what happens, as you could expect from a cosine. So basically, some regions it increases, so there is amplification in this region, and in other regions it is attenuated, so there is dissipation here, and they alternate like you see here. How can we understand this? So all is controlled by the spin angular momentum, as I mentioned. And because the two waves have different propagation constants, as they advance in space, the polarization is changing also as the wave propagates. And this is how it looks like. So basically, in the active region, you have a certain endness, in this case to the left, and it changes from linear to elliptical, circular, elliptical again. Then you get again linear at the top, where you don't get non-emission effects. And then you have dissipation, which means you have the opposite tenderness, the opposite spin angular momentum. Okay, so you see here clearly this chiral gain playing a role in this power beating characteristic. Okay, so I told you that there is this interesting link between gain and loss and spin. And now I want to show you that this has important consequences in the context of plasmons, of surface plasmons. So I believe you are familiar with surface plasmons. So there are these excitations that can occur at the interface between a dielectric on the top and the metal on the bottom. So regions with negative permittivity and positive permittivity. And plasmons have an interesting property, which is that they have a chirality. They have an intrinsic spin. And this spin of the plasmons is controlled by a property that is known as spin momentum locking. And what is the spin momentum locking? So it tells us that the spin of the wave, it's a transverse spin because the wave propagates, let's say, to the right or to the left, and it spins as shown by this arrow. And the spin is controlled by the momentum, which is the direction of propagation, multiplied, this is a cross product, by the attenuation in the dielectric region, the attenuation direction. So in this case, to the top, plus z. And this is the spin of the wave in the dielectric. So if you look at this property, it means what you see in the picture, which is plasmons that propagate to the left, they spin in a certain way that you can see in the picture. And plasmons that propagate to the right, they spin in the opposite direction. So there is a link between propagation direction and spin. Okay, if you change the propagation direction, you change the spin. On the other hand, I told you that spin controls non-emission effects if it's a chiral gain medium. And so if I replace the dielectric by a chiral gain medium, there will be a link between non-emission effects and direction of propagation because of the spin momentum locking. So we have what we call gain momentum locking. and what is gain momentum locking. This is nicely illustrated with the simulations. So here we have exactly the scenario I was saying. So we have a metal on top, and we have this chiral gain material here. For convenience, we picked the interface with the circular shape. No particular reason, just because we wanted to consider this scenario. And we excite the plasmons at this point, first on the top figure. So when you excite the plasmons on this point, they will propagate in the clockwise direction. And in this case, you can check using the spin momentum locking that the spin is anti-parallel to the gain vector, which in this case is along the y direction, coming outside the paper, I believe. And so because they are anti-parallel, the plasmons are going to be dissipated. So plasmons that go in the clockwise direction are attenuated, are dissipated. Now, if you do the opposite, if you put the excitation on this point, you are going to excite plasmons that go in the opposite direction, so anti-clockwise. And now, because the spin momentum locking, the spin changes the direction, which means it will be aligned with omega, and so we get amplification. Okay, so depending on the direction of propagation, the wave will be either amplified or attenuated, all this controlled by the chiral gain and the gain vector. Okay, so finally, I want to discuss quickly how we can realize these materials in practice, using specifically these buried dipole materials, which I will say a word about it, or chiral metals, which maybe it's a simpler description. And the idea is this, so transistors, so the idea is to use natural materials to engineer these transistor-like responses that I've been discussing. So far, just based on this idealized model that I told you about. And so let's consider first that we have a standard metal or semiconductor, so an electron gas. So the transport equation for a standard metal is this one, which is nothing but Newton's law. So basically you have the momentum or quasi-momentum of the electrons, it's P, and derivative in time of P is the electric force, Newton's law. You have here a dissipation term because of collisions with the ionic lattice, okay? This is a standard metal. And of course, for a standard metal, the current is related to the velocity through the charge and the density. Now, still for a standard metal, the relation between the momentum and the velocity is the effective mass of the semiconductor or of the metal, controlled by the curvature of the electronic band structure of the material, okay? Now, the interesting thing is that you have these chiral metals, that's why I'm discussing them, where you get an additional term besides the usual term, which is P over M. So this term is known as the anomalous velocity. And the anomalous velocity provides a coupling, a nonlinear coupling, as you expect to have a transistor-like response, between the momentum and the electric field, okay? And the coupling is what you see. And so basically you get a response that will be nonlinear. And now if you apply a DC bias, similar to the transistor, you can fix your point of operation, you can linearize, and you can see what is the optical response. It's the electro-optic effect, the linear electro-optic effect. So a few words before I move to that. So you see here there is a tensor, zeta. So this tensor is essentially what is called the Berry curvature dipole of the material. And it's determined, I will not say much about this, but it's determined by the geometry of the electronic bands, okay? Not just the curvature, but the geometry, and it's related to topological properties and with spin orbit coupling and so on, okay. So let me provide you an example. So first of all, when can you have this effect? You need materials with low symmetry. You need to break basically inversion symmetry. Otherwise, you don't have a linear electro-optic effect. We focus on materials with a very particular symmetry. It's the 32-point group. In this case, this tensor that I mentioned in the previous slides, D, it's diagonal, looks like this, so this Berry curvature dipole. So doing what I described, which is, let's assume that we apply a bias to the material, it's going to be along the Z direction, which is the symmetry axis of this 32-point group. If you apply the bias, you find that your linearized response looks like this. I'm going to explain it to you. Okay, so it's a tensor again. The diagonal terms, it's epsilon D. I told you it's a metal. Epsilon D is just the Drude response, nothing more. So along the diagonal, you have the Drude. And this is the response that you have if you don't apply the bias. Okay, so if you just leave the material by itself, it's a metal, so you get the Drude. Now, when you apply the bias, because of the nonlinearity, you get an additional term, which are the terms in yellow, and they are given by this formula, okay? Now, this type of response, you can notice, it's a gyrotropic response, very similar to the response that you get when you bias, for example, a metal with a magnetic field, okay? You don't distinguish them if you just look at the top. And because of this, we introduced something that we call an equivalent cyclotron frequency, because even though here we don't have a cyclotron frequency, because here we don't have a magnetic bias. Here we have an electric bias, okay? So this looks like a standard gyrotropic material at first, non-reciprocal, and indeed, we can have a Faraday effect. So you are all familiar, I believe, with the Faraday effect. So if you have this type of gyrotropic responses, if you have linear polarization, as it goes through the material, it is rotated because of this motion of the cyclotron orbits at the microscopic level. And indeed, it is well known. So tellurium is an example of these materials that I've been discussing. Actually, it's the better studied example, tellurium. And indeed, you can have this Faraday effect because it is triggered by the bias electric field, not the magnetic field. It's called the kinetic Faraday effect. And most importantly, this is not just theory. So indeed, this has been experimentally demonstrated already in 1979 and more recently other experimentations. And people indeed checked that you can induce this non-reciprocity with the electric field and engineer this Faraday effect. Okay, approaching the end, I'm not so much interested in the non-reciprocal properties, but on the chiral gain, which is the non-emission electro-optic effect, so related to this epsilon 2 primes that I told you previously. So we have our matrix that I showed you previously. We can find the eigenvalues and the eigenvectors. And similar to the case of the transistor metamaterial, the eigenvectors are going to be two circular polarizations now in the XOY plane that you see here. And these are the eigenvalues. So first, you can notice that you have the terms in blue. Terms in blue is the terms that are associated with the Drude model. I'm finishing. Terms in blue are the terms associated with the Drude model, so they are always there. They always provide dissipation, so they are always positive eigenvalues, dissipation for both polarizations. Now, the terms in black are the ones associated with the electro-optic effect, with the bias field. And if you apply a bias sufficiently large, such that omega c is sufficiently large, you can make this one become negative because of the minus sign. This one, there is a plus sign, so becomes more positive. And you can see it here. So with a strong bias, basically this one becomes more positive. And this one, there will be a region here, a spectral region, where it becomes negative. And here you have your chiral gain, okay? One polarization provides gain, the other circular polarization provides loss, okay? Exactly as in the example I showed you previously. This is my last slide. And this is a simulation. So this is based on simulations, based on the amplitude of the electric field in tellurium, where we find for a specific thickness of tellurium, the absorptance in tellurium as a function of the electric field for a fixed frequency. This is in the terahertz domain for the two polarizations. So for circular to the left, circular to the right. You see that as you increase the field, one of them, on average, the absorption increases. The other one starts decreasing on average, and if the field is sufficiently strong, it becomes negative. So this means that the material is indeed radiating energy, not absorbing energy, okay? So this concludes my talk, just a very brief summary. So I discussed with you a mechanism to engineer chiral gain, which is based on the combination of the static electric bias and nonlinearities. We suggested a specific physical realization based on this chiral metals that have this Berry curvature dipole. And finally, I didn't have time to discuss much of this. I showed you a few things, but chiral gain materials can have exciting applications in lasing, optical isolation, unidirectional propagation, and others. Thank you.
So thank you very much, Mario, for this impressive talk. So any question from the audience? Tony?
Well, thank you, Mario, for this really interesting talk and for being here with us today. Well, I have two questions. The first one is related to the first part of your talk, because as you know, I've been following your work on transistor-like metamaterials. So it is a simple question because you haven't entered fully in this part here, but in one of your first slides, you were mimicking the response of an NMOS transistor. Is that right? So
yes.
my question is, what would be the changes that you have to implement, or the physical or mathematical changes that you have to implement if you want to analyze a PMOS transistor instead of an NMOS type? Have you considered that?
We do not think about this. So if you just want to change the N channel by...
yeah, if you have the channel is N type, so it is NMOS. If it is P type,
I don't think
flowing
it would
holes
change,
instead of...
I mean, it's still through this, right? So it should still be true that the conductivity... So from the point of view specifically of the model, I don't think we would change something. Now, for NMOS and PMOS, well, for the two different type of channels, I think the characteristic that you have here is different, right? But we did not do much with this characteristic. We just assume that it's something that depends on the electric field like this, and we linearize. So provided it has this structure, it would not change anything. I suppose what it changes really just the specific shape of this curve. This would be my guess.
Yeah, we know that well, we have Fran over here. Maybe can. He works in electronics, but yeah, maybe the polarization should be negative. For instance, the DC polarization, right, and the connection to the substrate would be different. I don't know which would be the effects, but
I think in terms of the model, I have the impression it would be the same model.
It would be practically the same, but maybe the flow of holes instead of electrons.
That's for sure.
Can change, some parameter. So thank you for the answer. The second question is related to one of the chiral gain plasmons that you were showing. Actually, you showed that there is if you put a clockwise movement of plasmons, you get a gain, and in the anti-clockwise you get loss, or the opposite. I don't remember. So my question is, what would happen if you place like an obstacle in between where you have reflection? So can this reflective, for instance, if you put an obstacle in the upper part, so you would have naturally reflected waves. Do you expect that the reflected waves will follow the same trend, or can you use the reflected waves to be amplified or somehow, because the polarization can change or something similar?
No, so the plasmons will be attenuated. So if you have reflected waves that are plasmons, they will be attenuated. Now you can also have space waves, specifically in the chiral gain material, because this is not like a topological system. Okay, so this material is transparent. You can have propagation in the chiral gain material. So in the bulk region, there can be more things happening. Like I don't think there is any rule I can tell you. So anything can happen. But for the plasmons, basically the gain and loss are locked to clockwise or anti-clockwise.
They're not okay. Perfect. Thank you.
Yeah.
Thank you. Miguel?
Thank you, Mario. Very, very interesting talk. And my question is about the last realization, the last result, the very last result that you showed with the tellurium. About the curve that you were showing, where we have dissipation and gain at the end, the last plot. Yeah.
Yep. Yes.
So yeah, first thing, what was the origin of those ripples?
This is Fabry-Perot.
Fabry-Perot. Okay.
Yeah, because we take into account. So basically, what you're seeing there is Fabry-Perot resonances.
Okay, and just to make sure that I understand this correctly, so where you have the gain, then it's like you are having the transistor response that you wanted.
Yes.
So under the small signal approximation,
yes,
you are claiming here that you have like a transistor, a piece of material, tellurium in this case, which with the proper biasing, you can amplify the signal from the input to the output. And you said this is working at terahertz.
It's working at, so by the way, experimentally, the only thing that has been demonstrated is the non-reciprocity. And to tell you everything, this requires a field that is about 10 times larger. So I'm not even sure this can be done in tellurium because it may be too much heat. But tellurium is, so basically there is this parameter that I discussed with you, that is this Berry curvature dipole. It's quite small in tellurium, it's like 10⁻⁵. People have shown engineered materials with this like easily 1,000 times bigger, I suppose even 10,000 times bigger. And so you can have much stronger effects in engineered materials. And in that case, you don't need so strong bias, you don't have so much dissipation. So one concern for these materials, so if you were going to have a transistor mathematics, I mean, we're all familiar with electronics. We know that our computers get warm quickly, so they dissipate a lot of power when you have transistors. And here you have a bulk material dissipating a lot of power because there is a current flowing in the material. And so feasibility is always, you always need to ensure that the material can withstand the current necessary to have the gain. So tellurium is not necessarily the best option to have gain. I have the impression probably it's not doable with tellurium, at least with this p-doped. Actually, I said 10 times, it's not true. It's 100 times for the p-doped. There is another tellurium, which is n-doped. In that case, it's 10 times.
Okay. In any case, I get the main plot of the idea, and I think it's very interesting. What you do here is with the intrinsic properties of the material.
Yes,
so,
exactly.
Then just the next question is, could you just enhance the effects by, using metasurfaces, metamaterials?
Yeah, it's these engineered materials that I was saying, like superlattices. They're called superlattices. Yes, exactly. That's exactly that. So tellurium, for example, if you want to have an idea, the reason why there is this special, the chiral gain comes from the fact that the microstructure of tellurium is essentially like some helical type organization in the unity cell. And so it's this helical structure that creates this anomalous velocity and so on. Well, together with this spin orbit coupling, but okay. Yes.
Thank you very much. Very, very interesting. Thank you.
Okay. Any other one? Okay. Just to finish, I have a minor question. It's referred to the first part when you were talking about activation, depending on the kind of circular polarization. Maybe you have mentioned, but I'm not sure about the reason. So if you have one, let's say, circular polarization, one of the senses, you will have activation of the gain, and the other one you will have activation of the losses. And you have mentioned that when you have a plane wave, you have nothing or almost nothing. But I was wondering about, at the end, a plane wave is a sort of combination between LCP or one of the senses of circular polarization and another one. So wouldn't you expect to have kind of none? Not really. What is the mechanism?
I mean, it's not. This is an. I mean, if you look at the dissipated power, it's a quadratic form. It's not a linear form. So you cannot think in terms of decomposition. I believe. I think this would be my the simplest answer. But anyway, you see it from here. So if you have linear polarization, basically E is real valued and D cross E is 0, so the spin is 0.
Okay.
And so if you insert in the formula, immediately you get 0.
Okay. Yeah. So thank you very much.
Thank you,
Mario.
Thank you.
Well, just to finish, thank you to everyone to have come to see this seminar. Well, till the next time. Thank you.